Imagine this, a burst of energy from space so powerful it ripped through our galaxy, and when scientists caught it, it made them question everything they thought they knew about the universe. This wasn't just any cosmic event, it was a challenge to reality itself. In the next few minutes, we are going to dive into this mind-bending phenomenon, break down what it means, and why it should make you look at the night sky a little differently. Stick around, because this story is as wild as the universe itself. In the quiet hum of a scientific facility, something unusual happened. Instruments, designed to measure the fabric of the universe, started picking up signals that defied explanation. These weren't just blips or errors, they were consistent, repeating patterns that didn't fit any known models. Scientists, accustomed to the predictable dance of data, found themselves staring at readings that seemed impossible. It was as if the universe had suddenly decided to speak in a language they didn't understand. The instruments in question were highly sensitive detectors, built to pick up the faintest whispers of cosmic events. They were calibrated to measure the ripples in space-time, the echoes of distant collisions, and the subtle shifts in the universe's fabric. But what they registered was different. It wasn't the expected pattern of a gravitational wave or the signature of a known astronomical phenomenon. Instead, it was a series of spikes and dips that didn't match anything in their databases. The data was clean, the signals were strong, but the interpretation was elusive. At first, scientists thought it might be a malfunction. They checked their equipment, recalibrated their instruments, and ran diagnostics. But the signals persisted. They tried to account for known sources of interference, like radio waves from Earth or cosmic rays from space. They considered the possibility of software glitches or data corruption. Yet, after thorough investigation, they were left with the same inexplicable readings. The instruments were working perfectly, but the data they were collecting made no sense. This was a moment of profound uncertainty. Scientists are trained to trust their instruments, but they're also trained to question the unexpected. The data was real, but the implications were baffling. It was as if the universe had thrown them a curveball, challenging their understanding of reality itself. They found themselves at a crossroads, torn between the comfort of established knowledge and the thrill of the unknown. The initial detection wasn't just a scientific anomaly. It was a catalyst for a deeper, more fundamental questioning of the cosmos. In the vast expanse of the cosmos, scientists rely on observatories scattered across the globe to piece together the mysteries of the universe. These observatories, equipped with cutting-edge technology, often work in harmony to provide a coherent picture of celestial events. However, there are instances when these observatories report incompatible results, leaving scientists scratching their heads and questioning the very fabric of reality. Take, for example, the measurement of the Hubble constant, a value that describes the rate at which the universe is expanding. Different methods and observatories have yielded different values for this constant. Ground-based observatories and space telescopes, each with their unique strengths and limitations, have reported measurements that don't quite align. This discrepancy isn't a minor glitch. It's a significant inconsistency that challenges our understanding of the universe's expansion and its underlying physics. The situation becomes even more perplexing when considering the observation of cosmic events like gravitational wave detections. These ripples in space-time, caused by massive cosmic collisions, are detected by observatories like LIGO and Virgo. While these facilities have made remarkable strides in astrophysics, they sometimes report conflicting data. For instance, the exact location and nature of a gravitational wave source can vary between different observatories. This isn't just about pinpointing a cosmic address. It's about understanding the fundamental nature of these cataclysmic events. Such conflicting measurements force scientists to grapple with the limitations of their instruments and the complexities of the universe. It's a reminder that even with advanced technology, our understanding is still evolving. These discrepancies aren't failures. They're opportunities to refine models, improve technology, and perhaps even uncover new physics. After all, the universe is under no obligation to make sense to us, and it's through these challenges that our understanding grows. In the vast expanse of the cosmos, there are events that push the boundaries of our understanding, challenging the very models that scientists rely on. One such event is the observation of ultra-high-energy cosmic rays. These particles, which originate from outer space, have energies far beyond what can be achieved in even the most powerful particle accelerators on Earth. When these cosmic rays collide with Earth's atmosphere, they create showers of secondary particles. The energies involved are so high that they don't align neatly with the predictions made by our most established physics equations. This discrepancy has left scientists scratching their heads, questioning whether our current models are missing something fundamental. The standard model of particle physics, which has been incredibly successful in describing the fundamental particles and forces, starts to show cracks when dealing with these ultra-high energy cosmic rays. The equations that govern particle interactions at lower energies don't seem to hold up as well at these extreme scales. For instance, the energy spectrum of cosmic rays follows a power law, but there are deviations from this pattern at the highest energies. These deviations suggest that there might be new physics at play, something that isn't accounted for in our current models. It's like trying to fit a square peg into a round hole. The pieces just don't align. Moreover, the origins of these ultra-high energy cosmic rays are still shrouded in mystery. They are so energetic that they should be deflected by the magnetic fields in the cosmos, yet some of them appear to come from distant galaxies. This poses a challenge to our understanding of cosmic magnetic fields and particle propagation. Scientists have proposed various theories to explain these observations, ranging from exotic particles to new fundamental forces. However, without more data and a deeper understanding of these phenomena, it's difficult to say which, if any, of these theories is correct. The breakdown of known models in this context underscores the need for continued exploration and innovation in the field of particle physics. In the realm of scientific exploration, anomalies often serve as catalysts for deeper understanding. One such anomaly, observed in the cosmic microwave background radiation, initially seemed like a mere glitch. Scientists attempted to correct the data, assuming it was a result of instrumental error or miscalibration. They recalibrated their equipment, adjusted their models, and ran numerous simulations. However, each attempt to correct the data only exacerbated the anomaly, making it more pronounced and perplexing. The anomaly in question was a series of unexpected temperature fluctuations in the cosmic microwave background. These fluctuations, known as the axis of evil, defied the standard cosmological models. Scientists expected a uniform distribution of temperature variations, but the data showed a distinct pattern, almost as if the universe had a preferred direction. This was unsettling, as it challenged the fundamental principle of isotropy, which states that the universe looks the same in all directions. Recalibration efforts involved fine-tuning the instruments used to measure these fluctuations. Scientists adjusted the sensitivity of their detectors, recalibrated their frequency bands, and even changed the physical orientation of their equipment. Each recalibration was meticulously documented and cross-verified. Yet, the anomaly persisted, and in some cases, it became more pronounced. This was baffling, as recalibration should have either corrected the anomaly or confirmed its existence. The situation became even more intriguing when different teams of scientists, using entirely different instruments and methodologies, reported similar anomalies. This ruled out the possibility of a single instrument malfunction. The consistency of the anomaly across different studies suggested that it was not a result of measurement error but a genuine feature of the universe. This realization forced scientists to question their understanding of the cosmos and consider alternative explanations. Some proposed modifications to existing theories, while others explored entirely new frameworks. The anomaly, once dismissed as a mere glitch, had become a cosmic enigma that demanded a deeper understanding of reality itself. The scientific community was thrown into a whirlwind of confusion when an unprecedented cosmic event defied all known physical laws. Researchers worldwide scrambled to make sense of the data, their usual calm demeanor replaced by a palpable sense of urgency. Laboratories that once buzzed with routine experiments now hummed with intense discussions and late-night analyses. The event, which seemed to challenge the very fabric of reality, left scientists grappling with questions that had no clear answers. Conferences that were once scheduled months in advance were hastily organized, bringing together experts from various fields to share their findings and theories. The atmosphere was electric, a mix of excitement and trepidation as they delved into the unknown. Secrecy became a common thread among leading research institutions. Governments and private organizations tightened security around their findings, citing the need to prevent public panic and misinformation. Leaks were rare, but when they did occur, they sparked a flurry of speculation and conspiracy theories. Scientists found themselves walking a fine line between transparency and discretion, a balancing act that was both challenging and necessary. The event's implications were too profound to ignore, yet too uncertain to share openly. This secrecy, while understandable, also led to a fragmented understanding of the phenomenon, with different groups working in isolation, sometimes even at odds with each other. Collaboration, usually a cornerstone of scientific progress, became strained under the weight of secrecy and urgency. Competitive instincts kicked in, with some institutions hoarding data and others resorting to back-channel negotiations to gain access to critical information. The usual channels of peer review and open publication were sidelined, replaced by closed-door meetings and restricted access databases. This shift was not without its consequences. Some scientists expressed frustration, feeling that the pursuit of knowledge was being hindered rather than helped by the secrecy. Yet, others argued that the stakes were too high to risk premature disclosure. The tension between these opposing views added another layer of complexity to an already bewildering situation. In the realm of astrophysics, few events have shaken the scientific community as much as the observation of certain cosmic phenomena that seem to defy our understanding of time and causality. These events have led to the proposal of temporary theories that push the boundaries of what we consider possible. One such phenomenon is the concept of retrocausality, where effects might precede their causes, challenging our linear understanding of time. Retrocausality is not just a theoretical whim. It has been suggested as a possible explanation for certain quantum mechanical phenomena. In quantum mechanics, particles can become entangled, meaning the state of one particle can instantly affect the state of another, no matter the distance between them. This is what Einstein famously referred to as spooky action at a distance. Some interpretations of quantum mechanics suggest that this action might not be instantaneous but could instead involve a form of retrocausality, where future events influence past ones. Another intriguing idea is the block universe theory. This theory posits that all points in time are equally real and exist simultaneously. In this view, the past, present, and future are all part of a single, unchanging block. This challenges our everyday experience of time as a flowing, dynamic entity. The block universe theory has been proposed to explain certain cosmic events, such as the behavior of particles near the event horizon of a black hole. In these extreme environments, the usual rules of causality might break down, and the block universe theory could provide a more accurate description of reality. These temporary theories are not widely accepted, and they are often met with skepticism. However, they serve an important purpose. They push the boundaries of our understanding and force us to question our assumptions. They remind us that our current models of reality might be incomplete. As we continue to observe the cosmos and uncover its mysteries, these temporary theories might evolve into something more substantial, or they might fade away. Regardless, they play a crucial role in the ongoing quest to understand the nature of reality. Scientists often find themselves in a delicate position when their research challenges widely accepted beliefs or ventures into realms that defy conventional understanding. This was particularly evident in the case of certain cosmic events that have left researchers scratching their heads and questioning the very fabric of reality. The results of these studies were often downplayed, not out of malice or disregard, but out of a genuine fear of public misunderstanding. The complexity of these findings can be overwhelming, and there's a risk that sensationalized or oversimplified interpretations could lead to widespread confusion or even panic. One of the primary reasons for downplaying such results is the potential for misinterpretation. When scientists delve into the mysteries of the cosmos, they often encounter phenomena that don't fit neatly into existing theories. For instance, the study of quantum mechanics has revealed behaviors of particles that seem to defy the laws of classical physics. If these findings were presented to the public without careful context, it's easy to see how they could be misconstrued. People might start to believe that the laws of physics are arbitrary or that reality itself is somehow broken. This could lead to a loss of trust in scientific institutions and a proliferation of misinformation. Moreover, the language of science is inherently precise and often counterintuitive. Terms like quantum entanglement or superposition don't have direct analogues in everyday experience, making them difficult to explain in simple terms. Scientists are trained to communicate with each other using this specialized language, but translating it for a general audience requires a different skill set. When researchers downplay their findings, it's often because they recognize the limitations of public understanding and the potential for miscommunication. They might choose to emphasize the uncertainties and the need for further research, rather than presenting a definitive conclusion that could be taken out of context. Another factor is the historical context of public reactions to scientific discoveries. Throughout history, there have been instances where groundbreaking findings were met with skepticism, fear, or even hostility. For example, the theory of evolution by natural selection faced significant backlash when it was first proposed. In the case of cosmic events that challenge our understanding of reality, scientists might be cautious about repeating past mistakes. They may prefer to wait until the evidence is more robust and the implications are better understood before making bold claims. This cautious approach while frustrating for those eager for answers, is often a necessary step in the scientific process. It ensures that the public is informed in a way that is accurate, responsible, and respectful of the complexities involved. The discovery of quantum mechanics in the early 20th century sent shockwaves through the scientific community. It forced researchers to rethink the very fabric of reality. This wasn't just another theory to add to the bookshelf. It was a complete overhaul of how scientists understood the universe. The implications were so profound that they changed research approaches permanently. Before quantum mechanics, scientists operated under the assumption that the universe was predictable and deterministic. If you knew the initial conditions of a system, you could, in theory, predict its future state with absolute certainty. This was the world of Newtonian physics, where cause and effect reigned supreme. But quantum mechanics introduced a radical idea: uncertainty. At the smaller scales, particles don't behave like tiny billiard balls. They exist in a probabilistic haze, their states described by wave functions that collapse upon measurement. This fundamental shift in understanding forced scientists to adopt new approaches. They had to embrace probability and statistics, tools that were once relegated to the sidelines. Experiments became more about measuring probabilities and less about predicting exact outcomes. The impact wasn't just philosophical, it was practical. Researchers had to develop new techniques to study these elusive quantum phenomena. Technologies like the laser and the transistor, which form the backbone of modern electronics, emerged from this new way of thinking. Even the field of cryptography was revolutionized, with quantum encryption promising unbreakable codes. The shift also fostered interdisciplinary collaboration. Physicists started working closely with mathematicians, engineers, and computer scientists. This cross-pollination of ideas led to breakthroughs that might not have been possible otherwise. The study of quantum mechanics also changed how scientists approached education. Universities had to revamp their curricula to include quantum theory, ensuring that the next generation of researchers was well-versed in this new paradigm. The lasting impact of quantum mechanics is a testament to how a single cosmic event can reshape the scientific landscape. It's a reminder that reality is often stranger than fiction, and the quest to understand it is an ever-evolving journey. As we wrap up this mind-bending journey, let's recap the key points that have left scientists scratching their heads and questioning the very fabric of reality. We've explored how this cosmic event, a sudden and inexplicable burst of energy from the depths of space, has challenged our understanding of the universe. It's not just about the energy itself, but the implications it carries, how it might reshape our theories about dark matter, dark energy, and the fundamental laws that govern everything around us. This event has reminded us that the universe is full of mysteries, and every now and then, it throws us a curveball that keeps us on our toes. It's a humbling experience, really, to realize that even with all our advanced technology and knowledge, there's still so much we don't understand. So, what's next? Well, scientists are already hard at work, analyzing every bit of data they can get their hands on. They're collaborating across the globe, sharing insights, and pushing the boundaries of what we know. And who knows? Maybe one day, we'll look back at this event as the turning point that unlocks some of the universe's deepest secrets. We'd love to hear your thoughts on this cosmic mystery. What do you think it means for our understanding of reality? Drop your comments below and let's keep the conversation going. And if you're as fascinated by the unknown as we are, stay tuned for our next video. We've got some incredible stories lined up that will take you even deeper into the enigmas of the cosmos. Until then, keep looking up at the stars and wondering, because that's where the magic happens.